Okay, gang, welcome back. I think I will not quit my day job to become a Hollywood film producer, but I hope this is helping. One more section of new material before test 2, 5.3 on exponential functions. Really up until now, this course, the centerpiece of this course has been looking at different types of functions, starting with linear functions, then quadratic functions, then higher degree polynomial functions. What does a curve look like if you're looking at x to the 5th or x to the 6th or x to the 7th? Then rational functions. How about the ratios of polynomials and asymptotes? And now exponential functions. Yet a new class of functions that we'll introduce today. It's not terribly hard material actually, but it is a new group of functions that we'll spend a lot of time with going forward in the class. Exponential functions are basically functions in the form a to the x, where you've got a numeric base here. So this is a positive real number, not a variable, real number base, larger than 0. And then up here you've got your variable, or sometimes an expression in the variable, maybe a formula. What makes it exponential is that you've got change happening in the exponent, that x, or a formula in x, is in the exponent. So note, f of x equals x squared, it's got an exponent, but this is quadratic, right? This is just a parabola. It's got an exponent, but no x in the exponent. So that's not exponential. But f of x equals 2 to the x, where you put the constant in the base and the input variable in the exponent. Now this is exponential and is going to behave quite a bit differently than those polynomial curves. Let's look at a couple of examples. In fact, let's start with f of x equals 2 to the x. Maybe I can put it down here. If I raise 2 to the 0 power, I get 1. If I raise 2 to the first power, I get 2, or 2 to the second power, I get 4. But my domain is actually all real numbers here. I could also input -1 and get 2 to the -1 is 1/2. Let me plot those points roughly here on this set of axes. So I get 0, 1, and 1, 2, and I also put in 2, 4, and -1, 1/2. Sorry for the lack of scaling. I want to especially look at the points 0, 1, and 1, 2. Let me label those really well. Basically, if you think about what happens further down here, if you put in a smaller negative number, -10, you get 2 to the -10 is 1 over 2 to the 10th power, 1 over more than 1,000. But notice, although you get a little teeny fraction, it's not negative. So this is never going to drop below the x-axis. It's actually just going to be asymptotic to the negative x-axis this way. In this direction, I went to 2, 4, the next one would be 3, 8, 2 to the 3rd power. So this is going to grow very fast, 2 to the 3rd, 4th, 5th power. Powers of 2 grow extremely fast. I was just mentioning that 2 to the 10th would be more than 1,000. So this is a very characteristic shape for an exponential graph, with one of the tails asymptotic to the x-axis, and the other tail heading to positive infinity, growing very steeply. And note these 2 points, that actually, given that 0, 1 is going to be on a whole lot of these graphs, because anything raised to the 0 power is 1, and then 1 comma 2, you know, the base raised to the first power will be the base, 1 comma the base. Those 2 points are almost sufficient to get a decent sketch of this graph if you know how the tail behaves. Asymptotic to the negative x-axis and then growing very steeply through those 2 points. That's f of x equals 2 to the x. Let's consider f of x equals 1/2 to the x. I could look at 3, 4, 5, 6 as bases, but they don't behave very much differently than this. Let's look at a fractional base. Okay, a little bit of point plotting here. If I put in 0, 1/2 to the 0 is still 1. Look, I still get 0 comma 1. If I put in 1, I get 1/2 to the first power is 1/2. I still get 1 comma the base. So I'm going to get a point at 0, 1 and a point at 1 comma 1/2. Now let's think about what happens for some other inputs here. If I put in 4, a bigger positive number, 1/2 to the 4th is 1/2 times 1/2 times 1/2 times 1/2, that's 1/16. So 4 comma 1/16, oh man, that's about here. Notice that I can get really huge values of inputs here. They'll all be well defined, but big powers of 1/2 are just teeny little positive fractions. And this is not going to drop below the x-axis, but it's going to be asymptotic to the positive x-axis. So the tail over here behaves kind of like the tail did in the other direction. What happens if I put in negative values? Well, if I put in -1 or -2 here, 1/2 to the -1 is the reciprocal of 1/2 is 2. 1/2 to the -2nd power is 1 over the square of 1/2. Equals 4. So I'd get a point at -1 comma 2 and -2 comma 4. Basically, this graph just looks like the reflection of this one across the y-axis. And you notice you still have 0 comma 1, same point that was on this one, and 1 comma whatever the base is, 1 comma 1/2 in this case. And those 2 points, along with knowledge of the tail behavior, as long as this is a value between 0 and 1, as long as you have a fractional value here, then you're going to have asymptotic to the positive x-axis and growing as x goes to -infinity. That's not an increasing function, right? This one decreases everywhere. But in the tail behavior, you could say as x goes to -infinity, f of x goes up, the tail goes up. Okay? So let's generalize this. Let me hide my tracks a little bit. These basic exponential functions that just have some real number base raised to x without some expression in here really just have 2 different shapes. They either look like this, going through 0, 1, and 1 comma the base. So if this is a 7 to the x, this will grow a little faster, but basically the same shape. Asymptotic to the negative x-axis, growing very fast as x grows toward infinity. Or, this is basically, this is f of x equals a to the x, where a is bigger than 1. Or they look like that. Still go through 0, 1. Let's see, let me put that in a place where I can do all my writing. Still go through 0, 1, and they still go through 1.